engaged elsewhere. So his lectures will start next week, and that's the one on Friday. I'll send everybody an email to say this, but I thought I'd tell you that to start off with, because Professor Gibson and students' classes don't always end up in the same place. So I know he's away, and I'll tell you that now. So there are some lectures that I'm going to be doing on metals and metal pipelines, and then there are some laboratory practical classes where Dr. Euler will cover some basics of mechanical testing and metallography, so the metallurgy of steels, basically, and that leads to the assignment for this module, which he will give you. And then there are lectures on plastics from Professor Gibson. So that's the structure of the course. Now, there are a large number of lectures, and they're all on Blackboard, particularly the ones that I'm going to be delivering from you. There's a lot of material to cover, so I'm going to go through it reasonably quickly, but most of it's pictures, so hopefully that means that you'll be able to pick up an understanding. What I want you to get an indication of is that processing for making and joining pipes together to make pipelines changes their properties and changes things sufficiently that you have to test and check that you're doing it correctly. So it's not a lab, as in you're not going to be doing things. There will be a sheet with some questions on to do. It's a bit like an examples class. And then when we do the metallography a bit later on, you shouldn't need to do anything because the samples will already have been prepared. You'll be looking down microscopes at things. So you should be okay. A calculator might help. That's the only thing. Okay. So pipelines aren't new. I looked for the oldest picture that I could find, and this one came from a Chinese application for a long time ago. This is actually water pipes rather than gas pipes, but it's bamboo joined together just by inserting one hollow section into another. And you could make very long pipelines, a kilometre or so. The size of the pipe is just dictated by what you can grow. Now, bamboo is a very fast-growing plant, so you can get quite large tubes, but large meaning, 40 millimetres or something like that. It's not going to be incredibly large. In Europe, we didn't have bamboo quite so much, but we had plenty of forests, so people made pipes out of wood, and this came from barrel making technology. So people used to make containers for food and beer and wine, and if you make them very long, as you can see in this case, and you join them together, you can make pipelines. Again, you can make them for hundreds of meters, but it's quite expensive and quite labour intensive. So of course we wanted to develop pipelines out of materials that we could make relatively cheaply and long lengths and large diameter, and that's how the industry has basically developed. So the big change to pipelines really was the use of steel. And the reason that we could use steel is that people learnt how to join steel pipes together by welding. So there were cast iron pipes, particularly in the water industry before that. Cast iron is a strong but brittle form of an iron carbon alloy, whereas steel is strong and ductile. You can't weld easily cast iron, and so joints tended to be bolted or screwed together. So it's a very slow process for manufacturing a long pipeline, whereas steels can be welded. And steels really started appearing about 100 years ago, and for pipelines at least 70 or 80 years ago, so it's been around for a long time. But the steels have been developing over a period of time, and what I want to do in this first set of lectures is really talk a bit about how the steel's developed, the processing necessary, and how you would develop a material which can then be manufactured into a pipe. So before 1960, pipes were made from what we call semi-killed ingot cast steels. And what that basically means, it's a technical term for a bit of oxygen left in the molten steel, which was left there because it improved the yield. What happens generally is, if you're reducing iron ore in a blast furnace, you have to take iron oxide and turn it into pure iron. And if you spend a long time getting all the oxygen out, you had to wait longer for the furnace processes to take place, and that meant that you produced less steel per day. So if you decided, well, we can live with a small amount of oxygen in the steel, then it would mean that you were more productive. But the steel didn't have particularly good properties. The plate was hot rolled, so you take an ingot, which is a three-dimensional shape, and you put it through two rollers, and you roll it just like a rolling pin into a slab, and then you roll that slab into a sheet, which you then use for making pipes. The hot rolling process was about 1,000 degrees C. And although these steels were better than the other materials that were being used at the time, they still had relatively low strength because of the hot rolling process and relatively poor toughness. So they were easy to fracture because of the oxygen that was left within them. So this is a typical cast ingot. So this is a semi-killed steel, and you can see all these little bubbles here of oxygen or air that have been coming out of the steel. The fully killed steel, which is the one where all the oxygen comes out, we get this crater at the top, which you have to cut off. But this material was relatively free of bubbles and free of oxygen contamination. And an ingot is typically cast with approximately 20 tons of molten steel from a blast furnace, so it's a lot of material. And it's cast into a mould, and the mould is this sort of shape here. And you can see that it solidifies on the mould wall, which is cold, and then it solidifies here, and then it solidifies here, and then it solidifies here. And everything that's left over, the things that, impurities and things like that, end up being pushed into the middle here. So we get this, what we call primary pipe, going down from the top here, where all the impurities and the things that you don't want in the steel are the oxides and things. So you can cut that off. You cut it off here, you get relatively good ingot. But the composition here will be different to the composition here, because in the freezing process, the impurities are pushed ahead. So there'll be less impurities here than here than here than here, and there's a change in composition. So you have to generally heat the steel in a furnace at a high temperature to normalise the composition. That means homogenise the composition to make it the same throughout the whole of the ingot. So this is the primary casting, and then there will be a heat treatment process, and then there's your rolling processes and things. If you've got a semi-killed steel, you often get this secondary pipe, because again this is freezing, and this bit's been freezing faster than this bit because of the shape of the mould, you can see here, and you end up with a sort of defect right down the middle of the ingot. And this is the origin sometimes of defects that you'll see in pipe steel. You'll sometimes find laminations, little lacquer fusion defects right down the middle of the pipe. And it often comes from this primary steel making process and the fact that the homogenization process hasn't taken place and there's still a layer of impurities in the system. And we'll talk a bit about laminations later on. Actually, they don't have a big effect on pipes, so we tend to ignore them unless they're sufficiently large. But they are primarily a function of the steel making process. You can actually look at these defects, and metallurgists discovered over 100 years ago that if you took a cut section of surface and polished it to a mirror finish with various silicon carbide papers and diamond grits, and then you applied a very dilute acid, sometimes an acid in alcohol, you could actually reveal the structure of the material within the ingot. And here is an example of such a micrograph, and what you can see is these little cracks due to the segregation in the system. And you get cracks from the corners, you get these chevron cracks, and you get these V cracks all the way through the system. And they're basically driven by segregation and the cooling patterns. So that mould is wider at the bottom than it is at the top, so you would end up with a segregation pattern that points inwards towards the middle and top of the system. So what's segregation? Well, when you're in the steel making process, you have molten iron, but it has things like sulfur in it and oxygen, and manganese is added in the steel making process, so you get things like manganese sulfides and manganese oxides and iron oxides that are trapped within the material. And if they were kept in the liquid phase long enough, they would float up to the surface because they're less dense than molten iron, and then they're scraped off in a slag layer. But if they're very small, and if you don't hold at temperature for a very long time, they're trapped within the metal and they're just pushed ahead on the solidification front. So as it's solidifying, these little particles stay at the interface between the liquid and the solid, and they get moved in towards the middle. Eventually they get surrounded by metal, and then you get these segregation patterns. So what you can see here is like lots of little segregating things, and a crack has come along and has just joined it all up. And that is quite often the way that things happen. So by the 1960s, the quality of steel was recognised as being not good enough because of all of these things left in the steel. And steels were fully killed. So in order to get rid of the oxygen in the steel, rather than relying on the manganese, which had been originally used in the steel-making process, small amounts of silicon and aluminium were added. And they remove both any excess oxygen, and then they remove nitrogen that might be dissolved in the system. So to reduce the carbon content of steel, sometimes an oxygen lance blows oxygen at the surface of the steel, and it oxidises the carbon to CO2, and it's removed. So that's how you go from an iron with lots of carbon, 3%, to a steel with 0.1% carbon. But if you've got this oxygen lance, you can actually entrain other things like nitrogen into the steel. So it's not 100% oxygen, in some cases it's air that's blown there. And you need to have some way of dealing with the nitrogen and the remaining oxygen that you have in the system. So silicon and aluminium form very stable oxides. They're very thermodynamically stable. So they will gather up the oxygen quite nicely, and aluminium and silicon also react with nitrogen to form stable nitrides. So they can be reduced by that method as well. So this is done in the melt, so that by the time you get to casting, or continuous casting, and we'll talk about that later on, the properties of the material have been greatly improved. The plate is then normalised after hot rolling. So you hot roll at 1,000 degrees C before, and you then heat to 900 degrees C and cool in air. And that's what normalising is, making sure that the steel is above 900 because you want it to be a single phase austenitic steel at high temperatures, and then cooled in air to transform to the room temperature microstructure. And we'll talk about what these are later on. And what that does is it gives very small grains in a polycrystalline steel, much smaller than the hot rolled structure. And you could do that by reheating. You can hot roll, cool to room temperature, and then reheat to above 900 and cool, because undergoing the phase transformations on cooling and heating will help to refine the microstructure. So that was a very good steel, better toughness because of the small grain size largely, but still not particularly strong. So the only way you could actually increase the strength of the steels is to add alloying elements, chromium, nickel, vanadium, that sort of thing. Now that's great, puts the cost of the steel up, not so great, and makes it more difficult to weld, definitely not so great if you're going to make a pipeline. So all alloying elements that were added to steel at that particular time increased the carbon equivalent. CE here is carbon equivalent, and again we'll talk about that a bit more fully later on. But the more carbon there is in a steel, the more difficult it is to weld. So if alloying elements are equivalent to adding carbon, the steel's going to be more difficult to weld. So by the 1970s, we got steels probably that were strong enough for what we needed, but they were much more difficult to weld. And in this country, the 1970s was the expansion of the offshore, North Sea oil and gas. So a lot of these materials went into subsea pipelines. And that caused problems with weldability and things, and you had to work quite hard to make sure the quality was very good. So there was a driving force for improvement. So most materials are made now, in metals at least, in a continuous process because they are more uniform in their properties, and there's less batch-to-batch variation as the batch casting, which we talked about before. So in the previous case, I was talking about an ingot being cast, that ingot then being processed, rolled and turned into strip and then into pipes, and then another ingot would be cast, and then another ingot, and between each ingot there will be some variation in processing and some variation in properties. So people wanted to have a continuous process that they could tweak and control all the time to try and give the same properties. So that's where the continuous casting process came along. So the idea is that you have a ladle full of hot steel straight from the blast furnace, liquid, and that goes into a tun dish. And a tun dish, I think the best way I can describe a tun dish is it's like a bath with a plug that you can take in and out, which allows you to have a constant flow of molten metal into a mould. So we have a water-cooled copper mould, and this mould is shaped like a strip, or it can be shaped like a bar. It doesn't really matter. So in this case, you can see this is material that's coming out in bar shape. So it freezes on the surface and it's liquid in the middle, and then it falls a certain height, and then there's these rollers which gradually change it from the vertical to the horizontal, by which time it's completely solid on the outsides, and it probably is mostly solid in the middle, and by the time we get to the bottom here it's completely solid. And we've got a continuous process because you just keep filling up the tun dish. The tun dish is like the reservoir of molten metal, and we just keep putting it through. We can control the thickness by controlling the speed of these withdrawal rollers, which are pulling it, and the guide rollers here. We can control the cooling rates by spraying water onto these systems, and we can control the lengths of the product and the thickness of the product by the rate at which we pull things out. And then we've got a torch just to cut it off at the end. So we're producing by one process with a constant set of process parameters a product form which comes out, and if it's a strip will come out, be coiled up, and then the coil will be sent off for subsequent processing at a part of the steelworks that makes product form. So the pipe mill, for instance. So this process is widely used. Because of this bending, you can't have a material which is susceptible to cracking, so it has to have high enough toughness. So this process couldn't have been developed until the kiln steels came along that were higher toughness. But nowadays, almost all steels that are used in a plate or bar stock product form are made by this process. Special alloy steels still have to be cast in a batch form because the total volume of production doesn't justify this sort of process. So we had continuously produced material of fully killed composition, good strength, but the weldability needed to be improved. So what could we do? Well, from the 1970s, what are called controlled rolled steels were developed. Cold rolled doesn't mean rolled at fridge temperatures, below room temperature. It means that hot rolling was over 1,000 degrees C, cold rolling is less than 1,000 degrees C. So it's cold by the molten steel terms, but not cold by normal terms. So a silicon-killed, aluminium-treated and microalloyed steel, usually with niobium or vanadium, was rolled at temperatures down to 700 degrees C. And by rolling these steels, you can continuously refine the microstructure and make smaller and smaller grains. And these have very high strength and good toughness without having to add large proportions of alloying elements. So they have microalloying elements, less than 1%, but they don't have large amounts. And that means the carbon equivalent goes down, so the weldability is improved. So a pipeline steel is not a pipeline steel. A pipeline steel has been continuously changing over the years and will continue to do so, even if it has a particular strength, because the processing of that steel to get microstructures that deliver the good strength, toughness and weldability that we need have been changed continuously. And most recently, the hot rolling process has been controlled, the cold rolling process, or the colder rolling process has been controlled, and we have even put accelerated cooling by extra water jets on the surface to do it. I keep looking for pictures of hot rolled steel, but you don't see inside the rolling mills. You just see the heat. So this is a hot rolled steel slab coming out of the rollers. I can't show you the rollers, they're in there. Yeah, take it from me, they're over 1,000 degrees C, and there's not much you can do. You can't really get close to them. So you can see that's white hot. So that's a good indication. If it looks white or bright yellow, it's very hot. If it looks red, then it's probably in the cold rolling range. Hot rolling mill, huge mill. So there's a horizontal roller here and a horizontal roller here. Well, here and here, in fact. And then you can see the plate coming out. So that previous one was a slab. This is a plate. Slabs are about this thick. Plates are about this thick, or less. And it's big, and it's dirty, and it's messy, and it's heavy engineering. So here's the typical process for controlled rolling of steel plate now. And you can see we've gone from a single casting and single hot rolling operation to a multi-step operation. And basically the metals industry worldwide has improved process control and added to the complexity so that the microstructural control of the steel is what's needed for the application. So you're trying to make a material with exactly the right microstructure for that particular application. And that's what metallurgists have been doing really since the 1950s. But the improvements have been gradual over that time. So we start with a steel slab, about this thick, as I said, at least 150 millimetres thick, 6 inches in old money. Slab is reheated to 1200 degrees C, so furnace treatment. How long do we have to heat it? Well, we have to make sure that the whole slab is heated, so there's a certain soaking time that you need to put on. Then it goes through hot roll systems. And I've done a cartoon of the grains here. So individual grains are approximately spherical. In the steel, the steel's made up of individual crystallites with different orientations. The grains are quite large because at high temperature the grains tend to grow. Hot rolling reduces the grain size. If you put mechanical damage into a material, it reduces the grain size. We get recrystallization events taking place. And we want to have a material with a small grain size because that's a good way of introducing increased toughness and increased strength. So it's rolled in one direction, and then you turn the plate through 90 degrees, and you roll it in the other direction, so that's cross-rolling. And again, we've got this reduction in grain size. So it went into the rolling mill at 1200 degrees C. We haven't controlled the temperature by sort of reheating all the time, but by the time that process is finished, then we've gone down to about 1000 degrees C. So that fixes the time that you have. So normally this thing is rolled, rotated and rolled back, and that process will take a couple of minutes, something like that, which gives you this temperature drop. Then there is a cooling delay because the controlled rolling process we don't start until we get 900. So we start off with this grain size here, and we put it through a couple of rollers, and you can see the rollers reduce the size. These approximately spherical grains get elongated in the rolling direction. And then we go along, and then there's another roller here, and then even smaller grains, again elongated in the rolling direction. So hopefully, by the time you get to the final thickness, various steps of rolling have taken place, and the temperature is around 750 to 800. So about 200 degrees C drop for both hot rolling and cold rolling. So that's what you're trying to achieve. And to do that, the grain size is much, much smaller than the hot rolling case. And that's the key point to getting the good properties for this material. So, from the 1990s, to get the high strength steels, that's X70, X80 and higher grades, we needed to controlled roll and fast cool the plate by water quenching. So these are sometimes called accelerated cooled steels. Basically, if you leave a steel at temperatures of 500 or 600 or 700 degrees C, there is a tendency to try and increase the size of the grains. Grains have surface energy, and if the grain size is very small, there's a lot of surface energy in the material, and you can minimize it by increasing the size of the grains. So we try to avoid that process by cooling as fast as possible to keep the small grains that we've just spent a lot of money making. And when we go above X80, we also have to add a bit more manganese to the steel, and chromium and molybdenum, because we want to get the possibility of carbides forming in the system, and that will give you the higher strength, but then you've got to ask questions about carbon equivalent and weldability for these higher grades. So X80 I've always regarded as the tipping point. Up to X80 you can improve things by all these other processes and maintain the weldability. If you go much above X80, then the steels are inherently less weldable, but you may need to use that for other reasons in your applications. So what's the accelerated cooling process like? Well, it's quite straightforward. You have your continuous cast slab, you reheat, hot rolling, cold rolling, water spray, accelerated cooling, and then once you get down to around 300-400 degrees C, then you allow the diffuser cooling. Actually, the processes are quite straightforward, but controlling the processes to give you the microstructure that you want, that's less straightforward. And that's the skill of the steelworks. So how do we do that? Well, they tend to have these curtain cooling systems. So this is a water spray, and it's like a curtain of water that's going across. And you can see in this particular design, this hot roll, cold roll slabs coming out this way, and you've got 1, 2, 3, 4, 5, 6, 7, 10 curtains that it passes through to take the heat out. And by the time it gets to the end, it doesn't look hot, which is a good way of saying that the cooling is complete. Actually, it is still hot. When you go near that, you'd know that was more than 200 degrees C, but you wouldn't see it. Okay, so why are we going through all this effort? Why do we want to make this grain size so small? Well, again, metallurgists have been trying to develop new alloys and better materials for many, many years. And for steels, there are equations empirically that have been developed by taking all of the material parameters that have been measured and all of the alloys that have been looked at and fitting them to equations. So here is a equation for strength. So the yield strength is some constant plus a percentage of manganese times another constant, plus a percentage of silicon times another constant, plus the square root of the percentage of free nitrogen times another constant, plus a constant divided by the inverse of the square root of the grain size, and another constant which is a precipitation strengthening factor. So all of these factors make a difference to strength and toughness. So toughness, and this is in terms of the ductile brittle transition temperature, which we talked about before. Again, minus 19 plus something with silicon, something with nitrogen, again, square rooted, minus 11.5 divided by the square root of grain size, plus the percentage of perlite, we'll talk about what that means afterwards, and 0.26 times the precipitation strengthening factor. Now, if you look at all of those cases, if we make the grain size smaller, this value goes up. This is called the Hall-Petch equation, and it's very well known. In fact, this is one of the processes where metallurgy at Newcastle, and I say at Newcastle because I mean Newcastle, Australia, and Newcastle in the UK. Norman Petch was here, Edmund Hall was in Australia at Newcastle, and then they did the work which empirically showed that the increase in strength due to grain size is due to a constant divided by the reciprocal of the square root of grain size. Norman Petch then went to Leeds, and he did a lot of work at Leeds University as well, but he was here briefly. So you could say it's a Newcastle invention or discovery back in the 1950s. But the point about this is you can increase strength and you can increase toughness by making the grain size small. So that's why grain size control has been so important. So we maximise equation 1 by minimising equation 2, and we want the factors that benefit equation 1 having a negative effect on equation 2, and that's the small grain size. So pipe strength and toughness are improved by achieving a small grain size by normalising or controlled rolling. So if we can achieve the strength and toughness we require without adding alloying elements, we also can do that without sacrificing weldability. So this is like the holy grail for the pipeline industry. We want to have strength, toughness and weldability. If we can achieve that just by making the grain size smaller, we're not adding any alloy elements, so we're not adding cost. We're not changing the material properties and the microstructures and everything. So we've got no real problems when it comes to qualification because we still have the same materials. And so it's a very, very important way to actually go ahead. So small grain size is good. Smaller the better. So the pipe strength is increased by adding carbon and manganese. And some of the higher grades, they do that. All mild steel, every piece of steel that you get has carbon and manganese in it. Manganese is added in as a deoxidant in the steel making, and carbon is there obviously to give you the strength that you want. But you don't want to put too much, because both carbon and manganese will reduce toughness and weldability. So you have to have some carbon and manganese there, but you don't want to put too much. So microalloying was developed by putting precipitation elements in that can combine with carbon and nitrogen to form the little precipitates, which also increase strength. Again, if you put very small quantities of these elements in and have very small precipitates, it has a small effect on toughness and weldability, but a big effect on strength. If you put too much, then it's a problem. That's why we call it microalloying. These are added at the 0.2%, 0.3% level. They're not added at great percentages. Oh, and by the way, as we're talking about metallurgists here, that percent is weight percent. It's not atom percent. So all alloy designations are in terms of percentage by weight, not percentage by number of atoms. So I will only ever talk about weight percent in this course. So here's a microalloyed steel. So these are grains of ferrite, which is the low temperature form of iron, and you can see it's polycrystalline. There's another grain here, there's another grain here that's quite big. And the spots on the surface are the precipitates of niobium carbide that are used in this particular case. Now, what niobium carbide does when it's formed, if the temperature rises, this grain wants to grow, this grain boundary has to move. It can move until it reaches these carbides, and then the carbides sit on the boundary, and for it to grow more, it has to pull away from the carbide, and that means that the carbide particles act like little nails holding the grain boundary in place. So if you've done some rolling at low temperatures or high temperatures and you don't want the grains to grow, you put these carbides in and they will prevent that grain growth from taking place. If you go too high in temperature, the grains will grow because niobium carbide will dissolve. So this really only occurs at the bottom end of the rolling range, i.e. in the cold rolling range. So we stop grain growth from taking place by these carbides, and that also allows us to get grades above X80, so X100 and things like that. Let's look at steel development. This is just the composition of 3 different steels. This is the original semi-killed steels, the fully killed steels that were developed for continuous casting, and then the current cold rolled steels. Same grade. So you can see the composition has changed. What's happened over the years? Carbon content's come down. Well, we know carbon affects weldability, so that's good. Silicon content's gone up. That's because we've gone to a controlled rolled steel. Silicon does affect weldability, but at that percentage it's not a big effect. Manganese has gone up. That has an effect on weldability and strength as well. Sulfur, bad news, get rid of the sulfur. Yes, we can. So steels have much less sulfur in them nowadays, and that's one of the big sources of brittleness. Okay, we've gone for fully killed steels. Aluminium has been added, niobium and vanadium. Controlled rolled steels maybe don't need the vanadium because we've got the smaller grain size, so we can take that out. So the decrease in carbon and sulfur content with time has really driven the improvements in the properties of steels for pipelines at the grades up to X65, X70. And then when we go to higher grades, the use of microalloy elements has also been very important. So, what's a steel? What's cast iron? We have a very complicated diagram here, and this is what metallurgists love. They call them phase diagrams. And they tell you what you would find if you took a particular material with a particular composition. So in this case, we've got percentage carbon here, and at this axis we've got temperature. And if I had an iron carbon alloy with 3% carbon at 1500 degrees C, we'd be up here. That's a liquid. If I had an alloy with 1% carbon at 1000 degrees C, we'd be here, and we're in a solid phase range from a material called austenite, which is iron with a face-centered cubic crystal structure that can dissolve carbon up to 2%. If I had 0.1% carbon at 500 degrees C, we're in here, and we're in this range where it says ferrite and pearlite. Ferrite is body-centered cubic iron. It's what you get at low temperatures, and that can dissolve, that's this alpha in here, only about 0.04% carbon. So if we take iron at high temperature and go to iron at low temperature, we've got 2% carbon dissolved, or 1% carbon, it can no longer keep that carbon in solution. So by going from austenite to ferrite on cooling, you have to make some iron carbide, and that's the cementite Fe3C. And perlite is just a mixture of ferrite and iron carbide Fe3C. So by looking at this diagram, you can, and knowing the composition of the material that you've got, you can identify the main microstructural phases. And people have done that for many cases. And the good thing about iron, and the reason it's such a useful material, is you can heat from here to here and undergo a solid to solid phase transformation without melting or changing shape, and then go back again. So you can change the microstructure, you can change the properties of the material without changing its product form. Heat treatment of steel. And heat treatment gives you many more possibilities of doing things in a steel than you have in most other materials. That's why it's such a ubiquitous material and it's so good. In welding, of course, you go from here all the way up to liquid and back down again. So you're going to go through these phase transformations on heating and on cooling. And delta iron at the top here, which occasionally forms, that's the same crystal structure as ferrite. So you go from ferrite to austenite to delta iron. So structure, BCC, FCC, BCC, and then liquid. It's a bit more complicated. Generally, though, we forget about what happens here, because by the time we get into this range, everything's austenite. When Dr. Euler talks to you about metallography, there'll be a lot about what happens as we go up and down across this range here, because that dictates many of the properties of the steel. So if we look at a typical 0.1% carbon manganese steel, this is a structural steel with girders, bridge plates, pipeline materials. They all look similar to this. What we have, again in a polished and etched cross section, we have these white grains here and then these darker regions here. And when the first metallurgists looked at this, these dark areas shimmer a bit like mother of pearl, so they call it pearlite, ITE. And when they looked at this, this is pure iron as far as they were concerned, so fer for ferrous, and then ite, because it's a solid phase. So most solid phases in descriptions, the metallurgists call something ite. And that's what you can see on the surface there. So ferrite is iron, perlite is iron carbide, is it? No. Because if you go to a higher magnification, if we look at one of those little perlite colonies, what you can see is that the perlite is made of these dark bands and light bands alternating, like alternating cards in a pack of cards. And the darker bands in this particular case are Fe3C, iron carbide, cementite, cement, sticking the two layers together, you know, that was why they called it. And also it's a hard material, it's a ceramic, and alpha iron. So perlite is not a phase, it's a mixture of two phases, but it was incorrectly described as a phase by the first metallurgists because their microscopes weren't good enough to see this. So, the ductility and the toughness comes from the ferrite. The strength comes from the perlite. That's why if we put more carbon in, we get more perlite, more Fe3C in the structure, more strength. But this is good because the Fe3C is not as a big block of carbide. If it were a big block of carbide, it would crack very easily and steels will be brittle. And in fact, we know what big blocks of carbide do to steel because cast iron has big blocks of iron carbide, Fe3C in it, and if you make an iron casting and you hit it with a sledgehammer, you can quite easily fracture it into pieces. So we don't want big blocks of iron carbide. With perlite, the iron carbide is present in very thin layers and it's laminated structure, and this is a very tough structure, and this is very similar to the structures in seashells, what are called nacre, where you have a layer of ceramic and then a layer of a polymer and a layer of a ceramic, And the crack can go through the ceramic, but it stops when it gets to the polymer layer. And that gives very good toughness. And in this case here, the crack can go through the ceramic Fe3C layer, but it stops when it gets to the ferrite layer surrounding it. So it confers strength, but it doesn't reduce the toughness. In fact, it increases the toughness in some cases. So that's the microstructure of a typical structural steel, including a pipeline steel, before we start adding all the other alloying elements. You can see the grains here are quite big. These are 20 micron plus grains. Controlled rolling will take that grain size much, much smaller.
When the pearlite forms, it's not formed effectively as a single crystal, was there?
No, this is what we call a colony. So if you went into here and you went with a very high powered electron microscope, you'd find that there were lots of different bits of iron carbide, slightly different orientations, and you can get bits growing like this and like this and like this together. So if you go at a high enough magnification, it's single crystal, but that's true for everything. The other thing you have to worry about is what happened to all those nasty elements that you didn't want to deal with. So what happened to the sulfur? Do we remove it in the steelmaking process? Does it float up to the surface and be scraped off with the blast furnace slag? Well, no. Unfortunately, it doesn't. So if you polish the surface, in this case it hasn't been etched, it's just been polished, what you can see in a pipeline steel that's been rolled in this direction is that you get these elongated precipitates. And they're largely manganese sulfide, but they can also be pieces of silicate, which came out of the blast furnace linings that are mixed in with the metal and can't be removed. So they're all still there. And they tend to be elongated in lines, which we call streamers. Alumina silicates, again, blast furnace linings, and the insulators that are used in the steelmaking process. So you can get them throughout the steel. They've been managed. The sulfur on its own would be bad, but if you put manganese in and get manganese sulfide, that makes the sulfur's effect smaller. It doesn't remove it completely, but you're managing the impurity in that system. And that's what you do. This is a particularly bad steel, by the way. If I saw that amount of inclusions in the steel, I'd be saying reject, reject. You know, in fact, this is a steel from the 1960s. So that shows you where we started, really, with all these cases. If you see one inclusion in the field of view in a microscope at 400 times, that's probably okay. 50 is definitely bad. The other thing that I wanted to say, and what I'm going to finish with today very, very quickly, is to say that the phase diagram is thermodynamics. So it tells you what you would get if you left things a very long time. But unfortunately, in the real world, we have to process things as quickly as possible, so we don't necessarily get exactly what thermodynamics would tell us. And to illustrate that, we have what's called a time temperature transformation diagram here. So if you imagine this particular steel, this is a low carbon steel, if you heated it up to 900 degrees C and then quenched to 700 very, very rapidly and held it there, it would take about 1 second for phase transformations to start. So austenite is still stable here, and then we form some ferrite, and then we form some ferrite and pearlite, and it will be finished by the time we get to about here, 100 seconds. So we would get the thermodynamic stable material, which is in here, but we'd have to wait some period of time for doing it. If we cool so quickly that we got down to here, so we managed to miss all these thermodynamic transformations. With steels, you can get another material formed, a material called martensite. It was named after Professor Martens. He put the "ite" on the end of his name. And this is a very hard and very brittle phase of quenched steel. It's used for cutting tools, it's used in gears and bearings and things where we want very high strength. It is what often causes the failure in welds, because the martensite forms due to high cooling rates, because we've missed the thermodynamically stable transformations, we've cooled too quickly. And we want to try and avoid that. So, austenite and perlite, ferrite and perlite here, the normal structures. If we cool to 400 degrees C and held, we get another phase which is called bainite. And bainite is just a different mixture of iron carbide and ferrite. It has little particles of iron carbide rather than the lamellar sheets of iron carbide. Because it's formed at a lower temperature, carbon can't move so far, can't diffuse very far, because the temperature is lower. So we end up with a different microstructure. So the point I'm making about here is you have to consider thermodynamics, but you also have to consider the rate at which you're doing things. And that's what the steel companies have been doing to try and develop materials that are suitable for the pipelines. So I'll finish here. The next lecture I want to talk a bit more about martensite, because it is the problem that you're trying to avoid in many cases. And I'll also go on to talk a bit more about the development of steel compositions over time and what that's been driven by and what the effects actually are. Okay.